agenda. Good.
Yeah.
So this is the agenda for today's talk. Okay, this is not what I wanted. Let's stick with this. Okay, so I will present three papers, two of them published, one with a submitted revision on modeling COVID-19 data. The first one is a statistical model and has been published in Statistics in Medicine. The other two are more epidemiological type of models. The first one builds on an earlier paper in Proceedings of the Royal Society in 2018, and the application and refinement to COVID data has been published in BMC Public Health. And the last one, which is a metapopulation SIR type model, is under revision for Nature Scientific Reports, in the sense that we have submitted the revision. The first paper focused on Italian data, the other two on world data. And today I will mainly talk about the modeling aspects and not the computational aspects of these three papers. But let me tell you that the first one uses Markov-Chain Monte Carlo methodology, and the other two use approximate Bayesian computation, which was the topic of an earlier talk that I gave here at CISA. So, first paper is a statistical autoregressive model that we use to analyze 6 categorical data on COVID-19. And specifically, we model the susceptible, not previously ill, the recovered are the positive cases in quarantine, the hospitalized in ICU, and the deceased people. And as said, we model Italian data overall, and we also have a focus on Lombardy. So the observed counts for those 6 categories and over time are stored in random variables y, t, k. T is time and k is the category. And we put these counts in a vector of dimension 6. And the main assumption in this model is that the observed frequencies correspond to the marginal of a sequence of unobserved transition counts. So we let x, t, j, k, the number of individuals that at time t moved from category j to category k. So those x, t, j can be organized in a transition table. And you can see it here with the 6x6 table with the 6 categories that I just mentioned. And the first assumption of this model is that if we sum along the rows of this table, we obtain the count for that category at time t-1. If we sum along the columns, we obtain the count for that category at time t. So the marginals are observed. The table, the transition are not observed. So this table has some structural zeros. So because S is susceptible not before ill, those are zeros. And similarly, because D is deceased, if you're dead, you can just stay dead. So we have those structural zeros, and each one of these entries, as I said, is a transition count. So for example, xt35 correspond to the number of individuals who moved at time t-1, that were at time t-1 in category Q, quarantined, and moved to ICU. So hospitalized in ICU. We let the overall count n to be fixed across time. So we're assuming that Italy is a closed world. This is another assumption of the model. The second assumption is now how are we going to model the distribution of the random vector xtj, which is one of the rows in this matrix. So we have 2 type of model. We have a multinomial model and a Dirichlet multinomial model for this X. So we know the multinomial model is a generalization of the binomial model. So instead of 2 categories, we have k categories, in our case 6 categories. And we have those vectors of probabilities, which are the transition probabilities from category J to other categories. And this multinomial has some mean and some variance, which mimic the binomial mean n times p, except that here n is the count in that category J at the previous time point. And then we have a vector of probabilities. And the variance is n p times 1 minus p, but it's the generalized version of the multinomial variance. The other modeling framework that we have takes into account the dispersion of COVID-19 data. And this is a Dirichlet multinomial type of model. And the Dirichlet multinomial is an extension of the beta binomial model. In essence, instead of assuming the transition probabilities from categories to be a known fixed vector P, as in the modeling framework before, we assume that those probabilities are drawn from a Dirichlet distribution that is indexed by parameters alphas that do not need to be normalized. Those are not probabilities. So the mean and the variance of the Dirichlet multinomial distribution have this form. And here you can see that it's similar to the previous one. So instead of being n times p, or better, y at the previous time times the probabilities, here we have the same y as before, and the role of the probabilities are the normalized alphas, with alpha plus being the sum of all alphas. And alpha is a vector of dimension k, in our case 6. So if we let p in the multinomial model to be alpha divided by the sum of all alphas, the expected value of the Dirichlet multinomial and of the multinomial model are the same. And if we let this alpha go to infinity, the variance term in the Dirichlet multinomial tends to the multinomial one. So in a sense, this Dirichlet multinomial is a generalization of the multinomial case to allow for overdispersion. The third modeling assumption tells us how we are going to parameterize those probabilities. Under the multinomial model, the first model, we assume a logic parameterization of those transition probabilities, where betas are parameters where we are going to make inference, and f is a column vector that contains the term of either a polynomial or a spline of time of a suitable order. For example, if we take a third order polynomial, this f that is indexed by t, j, and k will be 1, t, t squared, and t cubed. And we're going to check which order of polynomial best fits our data. If instead of a multinomial model, we have a Dirichlet multinomial model, then what we model are not the probabilities, but the alphas. And because the alphas do not need to be normalized, we just assume that the alpha are e to the power and then f transpose beta. And while before we needed to constrain the betas to have identifiability, so we were imposing that the beta jj were zeros. Here for the Dirichlet multinomial, we don't need to do this, and we don't need the alphas to be normalized. Now, the resulting model is fairly straightforward in terms of interpretation, but fairly difficult to deal with because the distribution of the frequencies is obtained as a convolution of these product functions. So how do we estimate this model? Well, we take a Bayesian approach. We put some prior on the betas, and I'm going to show you results with diffuse priors, but we can also use informative priors. And moreover, we are going to put some also a priori constraints on the odds. So we let O, T, J, K to be the ratio of the probability of going at time t from category J to category K over the probability of staying in category J. And we put some lower and upper bound over some of those odds ratios. So those are all the priors that we're going to incorporate in our modeling framework. And then we use an MCMC algorithm. We first update the entries of this transition or contingency table, and then we draw the model parameter and we iterate over these two steps. Now, in order to update the contingency table, we select 4 entries in a sub 2x2 matrix of this transition, and we either increase or decrease the entries of this matrix, and we accept this move with a certain probability. And to update the parameters, we use a standard random walk metropolis step with a Gaussian proposal distribution and the usual metropolis Hastings acceptance probability. So using this algorithm, we simulate from the posterior distribution of the parameters in the table. And as the simulation goes on, at every time step of the simulation, time step S, we can also perform in-sample prediction of the frequencies Y of each one of the categories. And we can also do out-of-sample prediction. This is fairly straightforward. And at the same time, again, at every iteration of our Markov chain Monte Carlo simulation, we can also estimate the reproduction number, RT, using a ratio where at the numerator, we have the number of new positive individuals at time t, and at the denominator, we have a weighted sum of the number of new positive individuals up to time t minus 1. So this formula is adapted from a recently published paper to our context. Moreover, again, as simulation proceeds, we can compute some goodness of fit of our model. And we have a various discrepancy measure, both for the in-sample prediction, for the out-of-sample prediction, and also discrepancy that tells us how well we estimate each specific category of the K observed ones. And to do model selection, we use the posterior predictive p-values. I'm not going to go into the details of how this is computed. The important thing is that for in-sample prediction, we expect a value of these posterior predicted p-values to be close to 0.5. So I'm going to now show you the results of this model for the Italian data in the first phase of the pandemic. So we collect data from 24th of February until 24th of April, 2020. So 61 days of data. I'm going to show you the results both for the multinomial and the Dirichlet multinomial model, both for polynomials of order 2 and 3 for time, and with some constraints on the odds. So let me show you how those constraints are interpreted. For example, let's focus on Q, the quarantined. Here, what I'm saying is that if you're quarantined, the probability of becoming recovered or becoming hospitalized is more or less the same. On the other hand, the probability of going straight to ICU or dying is much smaller. So this is our those odds ratio interpreted, and our understanding of those transition probabilities helps us elucidate those prior opinions that we incorporate in our modeling framework. And therefore, the transition matrices that we need to explore are reduced in their space. Otherwise, it would be a huge number of transition matrices. Moreover, the results I'm going to show you incorporate 2 dummy variables to account for the effect of non-pharmaceutical intervention that were enforced in Italy on February 24th and on March 8th, 2020. So looking at the posterior predictive p-value, we see that the model that best fits is the Dirichlet multinomial with third order polynomials, either with or without constraints. Here you see that the p-value is the closest to 0.5. So from now, I'm going to show you results related to those two models. And we also can tell that the two categories that we are at best able to predict are ICU and deceased. And this was very important to us because predicting well the number of people in ICU is important during the first phase of the pandemic. So these are the type of plots that our modeling framework produces. So for each one of the observed time series, so we have the quarantine, the recovered, hospitalized, and so on. Before the dotted vertical line are the observed time series, and from that point on, we estimate, and we have the 95% prediction interval in gray. Moreover, we can also estimate the transition probabilities or the transition counts from each category to all the others. For example, let's focus again on the Q rows. This is the prediction from the 25th of April to the 26th of April, so one day ahead. And we predicted that of those in quarantine, some, about 2,665 recovered, 516 were hospitalized, and the remaining stayed quarantined. Not only we have point estimators, we also have credible intervals because we are Bayesian and we can produce 95% prediction credible intervals. And for quarantine, you see them here. And finally, we can produce an estimate of RT and the prediction from the 25th of April until the 4th of May. There are some summary statistics for the performance of the MCMC. We ran it for 500,000 iterations with a certain burn-in, and we have obtained a certain effective sample size, so everything works fine. Here are the trace plots. But as I said, I'm not going to go into the details of the computational aspects. So let me conclude about this first paper. I think it's important to have a prediction of these transition tables. Because we're Bayesian, we can incorporate prior information, we can quantify uncertainty. If you want to see our code is available in a GitHub repository, and this model can be used beyond COVID-19 data, but for other contexts where we have observed frequencies that may be conceived as sum of transition frequencies that are not observed. For example, electoral flows. So we know how many people voted for each party, and we want to infer how many voters move from one party to another is similar context. There are some limits of this model. It's essentially over-parameterized, and indeed the effective sample size for the parameters is not very good. The other point is that I've shown you the results with no covariates, but only with time polynomials as covariates. But the model allows the inclusion of covariates. So for example, we could include the number of vaccination. And the width of the prediction interval are quite large, and we are exploring how to restrict those prediction intervals. We use this model to perform also weekly predictions on the Italian data. And we enter those predictions every week on the European COVID-19 Forecast Hub. And we have been doing those predictions for the past 42 weeks, together with a bunch of other colleagues of other teams overall worldwide. And specifically, we predict every week the number of deaths and the number of new cases. And if you go on that website, you can see our predictions together with the ensemble predictions that is performed, pulling together, properly reweighting the prediction that each one of the research team that make this exercise produce. So I'm going to show you, for example, here the weekly predicted new cases prediction perform for the coming week. So they were performed on the 31st of January. So this is in dark gray are the ensemble prediction, which, as I said, is a suitable average of all prediction. And in purple here, you see our prediction. So we predict only 1 week ahead. Other groups predict both 1 week and 2 weeks ahead. We believe that our model is reliable 1 week ahead, so we don't go beyond 1 week. Here you see, again, for this week prediction, all the prediction submitted by, it's about 20 research groups. In Italy, there is also a group at Università di Pavia who performs prediction, and there is a group at Politecnico who performs prediction, and we all submit every week. So it's an interesting exercise. And so here, each color is a prediction from a different group. And here are the deaths, again, predicted for this week. Dark gray, the ensemble prediction, and purple is our prediction. Here you see that our prediction envisions a better trend for deaths than probably pretty much everybody else, because we are below the ensemble prediction. So let's see how we perform. So if we go back 1 week and we look at the new cases predicted for the past week, so we go back in time at 24th of January. Here you have the ensemble prediction, but also now you have the observed value. Okay, so the ensemble prediction is in dark gray. The observed value is this black line. And the black line is inside the credible intervals of the ensemble prediction. And here you also see our prediction relative to last week. It's hard to say, but so I'm going to focus. And you see that, so the observed is dark black. Our prediction was really very good, specifically last week. So we're very close. So these are the new cases. And similarly, we're fairly good also on the death. So this website also performs an evaluation of the different criteria that are of the predictions that are submitted by the different research groups. And there are different metrics. Let me show you two of them. One is the absolute error, which is the absolute difference between the observed value and the point prediction. They ask not only to do a point prediction, but also to provide quantize for our predictions. So they also have a weighted interval score, which is the weighted sum of the interval score for each central interval. So this penalizes forecast intervals that are too wide. And we are performing well relative to both these measures. These are, they also do a ranking of each team, and they use this to do their own ensemble prediction, because depending on how each team performed in the past, they're going to put more or less weight on their future predictions. So this is us. And last week, we were the best in terms of both these two measures. Then here is the Politecnico di Milano prediction. They typically do better than us. So I'm showing you last week because we did particularly well, both for new cases and for that, the number of deaths. So again, we were the best last week, but we are typically among the best 5 or 6 of those more or less 20 predictions. I'm gonna now move to SIR type of model.
So Antonietta, why do you think, what's the modeling assumption that made the model your model work better, do you think?
This is a tough question, because you should look at all other modeling assumptions, because we're not the only Bayesian. For example, here you see Università di Pavia that also has a Bayesian interesting Garch type model. But I think the fact that we incorporate prior information is important. And then the other thing that we do is the following: because we have more than one model, now the prediction that we submit are a weighted average of the predictions of each one of our models. So in a sense, we do model averaging before submitting our predictions. So we try, remember we had model 7 and model 8. So every week we estimate model 7, we estimate model 8 with polynomials of order 2, polynomials of order 3. And then typically we look at the predictions, we use our prior understanding of, how the pandemic is evolving, and we average those predictions based on our past performance. So in a sense, we do ourselves an ensemble prediction from our model. And I think this is important. Thanks for your question.
Thanks.
So we're now moving to the second paper. This is a paper, while the previous one was a paper with colleagues from Università di Perugia and Università Milano Bicocca. So it was an Italian effort. This second paper is a joint effort with Queensland University of Technology, a research group led by Kerry Mangerson. And the leading author is David Warren, who did a lot for pretty much everything for this paper. So this paper was published in BMC Public Health in 2020. So this is a more epidemiological type of model. So we have 3 categories: susceptible, infected, and removed. And we have a transmission rate alpha and a removal rate beta. Now, this is a standard epidemiological model, but we all know that is too simplistic for explaining the COVID-19 pandemic. So what we did is we modified it. First of all, SI and removed are unobservable compartment. So the susceptible, the infected, and RU, the unobserved, removed, here removed means both recovered or deceased. We assume that those are unobserved category. On the other hand, what we observed are the active confirmed, the positive cases, the recovered cases, and the diseased cases. So those are the observed categories. So as in the standard SIR model, we have a latent transmission rate alpha. We have an identification rate from the infected to the observed infected that are the active confirmed cases, which we call gamma. And then we have a case recovery, R here stands for recovery, beta, and we have a case death rate, delta. And then we have a latent removal. So those are people that got infected, didn't get identified as infected, for example, because they were asymptomatic or they didn't get tested, and either died or simply recovered from COVID-19, and we never got to observe them. And we assume that this latent removal rate is a scalar eta parameter that we're going to estimate of the observed removal rate beta. So this parameter now has 4 rate parameters, alpha, beta, gamma, and delta, and a scale parameter between 0 and 1. We also have an additional parameter K that is needed for initialization, because I0, the infected at time 0, we don't know how many there were. So we assume that there were a fraction K of the active confirmed at time 0. So this is an additional parameter K. So now to model the community response to the pandemic, instead of having a parameter alpha, which is the latent transmission rate, we model this latent transmission as a function G of the observable. So we have a function G of A, R, and D, which are the observed variables. And this function G induces feedback loop that tells us how each country reacted to the pandemic. So this transmission rate function G is made of two components. One is the regulated transmission and one is the residual transmission. So we have two additional parameters, alpha and alpha 0. And this function F, this regulation function that tells us how a community responds to the pandemic, we model it as 1/1 plus a utility function or a cost function of the observable. And an additional parameter N, which is a strength parameter, that is a positive parameter that tells us how strongly each country reacts to the pandemic. And to make things simple, this utility function, we take it as a simple function as a sum of the cumulative case numbers. So C is active, recovered, and deceased. So this is the cumulative case numbers. And so this function is simply 1/1 plus C to the power N. So let's focus on this N parameter. This models the community tolerance to rising case numbers. If N is 0, it means that the country does no regulation whatsoever. If N is large and bigger than 1, it means that the country has a low tolerance to the pandemic and acts strongly to it. On the other hand, if N is small and less than 1, it means that the country has a high tolerance to the pandemic and does not act strongly to stop the pandemic. So larger N results in smaller cumulated cases for regulation to take an effect, for the state or the country to start imposing non-pharmaceutical intervention or to impose vaccination and so on. So this is the model. So overall, we have a vector parameter, the alpha, the beta, the gamma, the delta. Then we have the alpha 0, the eta, this N parameter, and then K. And we estimate those parameters using the observed time series of from the Johns Hopkins University website. And we do estimate a separate model for each country. And we start modeling the data from the first 100 observed confirmed cases, cumulative. So this is time 0 for each country. So again, we are Bayesian. The model that I've just explained to you gives us the likelihood. Then we put a prior on each one of those parameters. I'm not going to go into the details. This gives us a posterior. Now, the posterior is intractable because the likelihood is intractable because we have those unobserved latent categories. And therefore, to estimate this model, we'll resort to approximate Bayesian computation, which is a likelihood-free methodology. So I will not tell you about ABC. This is something I covered for you. I think it was 2017 when I gave a seminar on ABC. I went back and looked at my slides. So if you want to know how ABC works, you can listen to that previous talk of mine. Let me show you some model fit. So these are the Italian data and the data from Iran. You see the 3-time series of observed. So we have the legend is here. Blue is active, red is deceased, yellow is recovered. And you see that here we do a fairly good fit. We also have the, so we have the predicted, which are the lines, the points, which are squares, circles, or crosses that are the observed, and we have the 95% credible interval. So overall, we have a good fit, except for some countries, and here are some challenges in the data arise. For example, this is China, and we know that China on February 13, 2020 changed completely the way of reporting cases, this circles here. This is South Korea. Again, we don't do a very good job in some of the countries, but this is good enough for our purpose. So at the end of the day, with data up to end of March 2020, we estimate each one of the parameters for each one of the countries worldwide that reported cases on the Johns Hopkins University. And here you see some plots where in the first plot, we plot the identification rate, gamma, against the response strength. And here you see that red countries, there are countries that at that time had many cases like Italian, Germany, Spain, have a very small identification rate. On the other hand, countries like China and South Korea that at that time already had not many cases compared to other countries, had a very quick recovery due to high identification rate. You see here, Korea and China, and low K. K, remember, is the ratio of undocumented to active cases at the first day when we observe 100 confirmed cases. So at the time they started reacting to the pandemic, we estimate that there were few undocumented cases. On the other hand, for example, in Italy or in other countries like Iran, Turkey, US, UK, there were this value of K was fairly high. We re-estimated the model on data up to mid-April, and we see, for example, in light of this new data, how many countries have a lower value of N. Remember, N is the strength to which each country reacts to the pandemic. And overall, we have a lower value of gamma, which indicates an increased testing and contact tracing capacity for pretty much all countries. So to summarize, this model allows us to quantify and characterize the community response to the pandemic worldwide. And we use this general regulatory mechanism that results in this feedback loop, so that we don't need to model how each country reacted to the pandemic, the timing and the measure, but this feedback loop allows us to take that into account implicitly. Many countries with large cases have a low value of this regulation parameter, so didn't react strongly to the pandemic, at least at the time we estimated the model. And rapid recovery from the pandemic typically corresponds to high identification rate and to a lower initial undocumented number of cases. And this is in line with what we would expect. And I mean, we used successfully ABC. It wasn't easy to set up, but it worked. And the last paper I want to tell you about is this paper, which is...
Sorry, it's again me. I have another question.
Sure.
Did you use just like ABC or like, because sometimes people with ABC refer to likelihood-free schemes in general, no? Like
no. So we use particle filter ABC. So it's not just the basic ABC, but it's not likelihood free. So it's really ABC is SMC ABC.
Okay, thanks.
Yes. So it's because one of the co-authors is Chris Drovandi, who invented the SMC ABC. That's what we used. And we were lucky to have him on board because he was taking care of these computational aspects. Thanks. Thanks for the questions. Any other question on this paper?
Maybe I have a question. So the effect of vaccination, which, okay, clearly this thing was not included because you did this analysis when this thing was not around. But, well, how would you actually model it in this framework?
I'm back to the original modeling setting.
Yeah.
And add an additional category among the observed one, because we know the count of people that got vaccinated. So I would have an additional compartment, which are the vaccinated. So of the susceptible people, okay, some get vaccinated. So there will be a vaccination rate. Of those vaccinated, some still get infected, and so on. So I would insert a category here of the vaccinated ones. And then
yeah, and then so you would have 3 extra parameters.
Yes.
Just to understand, because of course beta and delta would be dependent on the fact that they are vaccinated, no?
Yes.
All right.
Yes.
Thanks.
The recovery and the death rate, yes, would be depending on whether you are vaccinated or not. Yes, so we would have an active confirmed among the vaccinated and among the non-vaccinated. This is a data that is not reported. So from our official statistics, we don't know how many of the positive cases are vaccinated and how many are not vaccinated, right? But I'm sure this information is available somewhere. This is another issue with COVID-19 data. Not everybody gets to see all the data.
Thanks very much.
Yeah, thanks for the question. Okay, so the last paper. So we just recently submitted a revision to Nature Scientific Report. So this is a joint effort with the Queensland University of Technology of the paper that I just told you about, plus a team from Harvard School of Public Health, led by J.P. Onnella. Here, the leading author is Thien Lee. He really did an amazing job with this paper. So here we put, in a few words, the compartmental model that I just explained over a network structure. So this is a metapopulation SIR type model. So the question that we want to answer is to fly or to lock. And this is a well-known dilemma. Should we let our border open or should we restrict people flying in and out or moving in and out of countries? Well, there are economical, financial motivations. We know that COVID-19 has led to the largest global recession since World War II. The global economy shrank by 5.2% in 2020. More than 43 airlines have declared bankruptcy, and 193 out of 740 European airports are at risk of closing. And the travel restriction cost the global economy an estimated $400 billion every month. So, but in order to prevent the pandemic to spread, many countries enforce travel restriction to avoid importing undetected cases. So those travel restrictions have been proved to be effective in the early stage of the pandemic, but not in the later ones, and may help delay the pandemics up to 4 to 6 months. But from the very beginning of the pandemic, the WHO advised against international travel restriction, but still many countries have nevertheless those travel restrictions. So the question is why there are so many travel restrictions? Well, the reason is because as it is, the recommendation are of the form you're allowed to travel or you're not allowed to travel, or if you're coming from a red country, you have to quarantine if you travel to another country. So this is a questions that we're trying to address. So when travel restrictions are effective, and how can we go from a yes and no type of regulation to a more effective strategy? So the goal is to propose a framework for assessing airline travel restriction that simultaneously controls the pandemic on one hand, and on the other hand, avoid damage to the global economy. So the framework consists on the compartment model that I just told you about, that we use for each country worldwide, plus a global network metapopulation model that connects each country through airline traffic. Again, we use an approximate Bayesian computation strategy to estimate the model parameter. And the goal is to assess the airline travel regulation policies and to possibly come up with better ones than the existing ones. So the local epidemiological model I just told you about basically tells us that for each country, we have a vector of susceptible, infected, active confirms, recovered, diseased, and removed undetected. And to go from time t to time t plus 1 for each country, we have a Poisson distribution that tells us how those counts are increased or decreased. For example, the susceptible at time t plus 1 are the susceptible at time t minus a Poisson random variable that has a specific rate that depends on the alpha parameter. Similarly, the infected at time t plus 1 are the infected at time t plus this y1 minus those that are diseased and those that are recovered, and so on. So this is a different way of telling you about the same model that I gave you before, in a more formalized. But here you see the alpha, the gamma, the delta, the beta parameter that we had before. Okay, so how do we put this into a global metapopulation model that combines those local models through the airline traffic data? Well, we do this in 2 steps. As I said, for each country I, we have a state vector at time t and a set of parameters for that country. So at step 1 of our modeling framework, we evolve the internal state for each country. So country I goes from time t to time t plus 1. Then we incorporate travels. So xi at time t plus 1 move to xi plus at time t plus 1. And this xi plus takes the flying in and the flying output from and to that country. And those flying in and flying out can increase the susceptible and the infected of that country. So we're assuming that people don't fly, people that are active confirmed do not fly, and in fact they cannot fly, they should stay quarantined. And so the people that fly in and out are going to either increase or decrease the susceptible and the infected of each country. So x plus is equal to x, taking into account the flying in and the flying out. Again, we estimate the model through, this time we use the replenishment ABC, again by Drovandi. I'm not going to go into the details of the ABC model. I'm just going to show you how for each country the model fit. So here you see US. The first plot is the confirmed cases. The second plot is the deceased. In red, you have the data. In blue are the fitted values, and the shaded regions are the 95% confidence interval. So for most countries, we do a good job. For some countries, you see, again, problems with the data. For example, this is France, and the red line that I'm pointing you to is the accumulated confirmed cases, which of course cannot go down in time. So these are problems with the data. And this is one of the major issues with COVID-19 data, but let's not talk about that. In any case, so we fit for each country its compartmental model with its own parameter. And then we consider the flying out and the flying in. So the x plus is equal to the x plus who flies in and who flies out. And we regulate the inbound travel by letting the proportion of travelers that enter each country vary. So we add an additional or a set of additional parameters, P, J, I, T. So those are the proportion of peoples that are allowed to fly from country J to country I at time T. So if this P is 0, then this means complete shutdown for that country. That country does not allow people to fly in nor to fly out. If this parameter is 1, on the other hand, this is a fully open country. Everybody's allowed to fly in and out. Now, we study 8 different policies. Besides the fully open and the completely closed policy, we have studied setting where countries require 40 days quarantine for all arrivals. like India or Korea, or countries that require 40 days quarantine only for arrivals from high-risk countries, those coming from the red zones, like also Italy, UK, Switzerland did that. And besides studying those existing policies, we suggest 2 additional regulation strategies. The first one is what we call the average control. Here, the average number of undetected cases each day in the next time horizon, capital T, has to stay below a certain threshold. In the probability control, on the other hand, we require the probability of the number of undetected cases in the next T days to stay below a certain threshold. That stays below a threshold, the probability is at least a given pi value. Okay, so I'm not going to go into the details, but what I want to show you is that, well, first we investigated the effectiveness of the coordination of the adoption of these strategies. And right now, each country is deciding what to do. We showed that, of course, if we could coordinate, for example, at least inside Europe, everybody would be better off. We estimate the model with data from January 1st to May 31st, 2020, and we predicted for the first 2 weeks of June. And we used real data from traveling in and out countries that were given to us for free by, let's see, I didn't mention that, maybe I should mention, Official Airline Guide and Open Sky Network. So we use this data, some is open and some was given to us for free for research purposes. So what is interesting is that with our proposed strategy, and here I'm talking about the average control strategy, only 33%, we can allow 58% of the airline travel still with a situation of confirmed cases and active cases to be the same as the fully closed strategy. So in this table, you see that the proposed strategy and the fully closed strategies. In the first row, you have RU, which is are the confirmed and unconfirmed cases, and RA, which are just the confirmed cases. And the first column is 2019, where everything was fully open. Then we have the data in the first months of 2020, where the airline was cut by 33%. And we observe a certain reduction in the number of cases. Then we compare with the fully closed and the proposed strategy. So with the proposed strategy, we allow 58% of the traveling still having the number of cases compatible or at the same level of the fully closed strategy. So this is the end of my presentation. To conclude on this last paper, well, first of all, we would like, or actually the referee is asked to further simplify the proposed policy and further investigate its effectiveness. We can again incorporate vaccination in the model, as Alessandro was suggesting, and we can further make the epidemiological model even more complex. Besides including vaccination, we can include more compartment. And ideally, we would like to also consider the multiple virus variants that are that have appeared and hopefully will stop with Omicron. Thanks for your attention. I'm happy to take additional questions if you have any.
Maybe I can start with one. I would actually have many. The so the thing is, the quality of the data that come from different countries are typically very different. It's not only a matter of numbers, but also of reliability. No? Did you somehow try to take this into account? Like, for example, the number of so the level of censoring, I talk about it in statistical sense, not that there is any, so the number of data which are basically unknown. I haven't understood if you have taken this into account in the third model in some manner. While in the first case, it's clear that you are fitting data independently for each different country, so you have different confidence bar, but in the other case, you have everything in communication, and so, well, in a way, the different level of confidence on the different data should play a role, right?
Yes, it does play a role, of course. We don't model it explicitly, so we don't have anything that tells us this data coming from this country are more poor than other, or different definitions, of course, of number of cases, how disease are reported, and so on, implicitly. So if the counts of, for example, the death and the recovered is not compatible with the active confirmed that that country reports, we implicitly think that those are infected unobserved. Okay, and similarly, again, we implicitly consider the removed unobserved as an unobserved compartment. So if a country underreports the number of diseased, they end up in the removed unobserved. Okay, so those unobserved category, in a sense, take implicitly into account the fact that definitions are not uniform across countries, first, and second, that there are problem in reporting the data.
Okay, thanks.
But so we don't do it explicitly, but in a sense, we take that into account implicitly.
I have a question more related to the, let's say, outcome of these works. I was wondering whether you use, I don't know, interact with some people to try to enforce some policy making using this data, or I don't know whether this is more, let's say, research and speculation.
Okay, thanks. Interesting question. So the third paper was motivated by the fact that Anthony Fauci visited the Harvard School of Public Health and specifically said something along the lines. Actually, in the previous version of the talk, I actually reported what is actually said, but let me read it for you. So he said, I think that the binary approach that either you are locked down or you are let in, or you let in all fly is not efficient. There is a place in the middle where we can open the economy and still avoid these kind of surges that we are seeing. So this was August the 5th, 2020. And so this is what has motivated JP Onella, colleague and friend for Harvard School of Public Health, to investigate this. And I know that he has discussed there at Harvard School of Public Health with colleagues that handle public health, and some of them are involved in decision committee and strategies. And so he discussed it with them. I didn't do it personally. But yes, hopefully the paper will be published soon, and Nature Scientific Report is a good venue for the journal, so it will get visibility. And so hopefully those policies that are more compatible with, the economy not being completely stopped but still the pandemic not evolving as fast as it is or as it was to be enforced. Thanks.
Thank you.
I'm curious to know if there's anybody in the audience who is involved in any modeling of COVID-19 data.
I mean, Alessandro Laio is my supervisor, and we have some COVID-19 data, but completely different scale. We got data from a doctor in Udine about patients and about their outcome. And we're trying to predict with some variables that can be measured in the beginning when somebody enters the hospital, how bad their case will get of COVID. So it's COVID data, but a different one.
Yeah, thanks. Yes, I know Alessandro is doing this. Thanks. Yeah, this is also very interesting. I also helped a hospital in Pavia to predict, actually using the same model I showed you for Italy. The exact same model was used to predict the number of occupancy of beds in ICU or regular wards in Ospedale di Pavia. And what's interesting is that there, we also had the data of the matrix. We could observe the transition matrix because the hospital knows, you know, how many patients arrive in the emergency room and every day how they go to hospital ward, ICU, how many recover, how many are dead. So that was a simpler problem where we didn't have to impute the transition matrix, but the transition matrix was observed. But the same model applies. Because again, the row sum and the column sum are the people that today are in each category and yesterday were in each of the categories. So the categories were emergency room, regular ward, ICU, deceased, and dismissed, meaning recovered. Okay, so we use the exact same model and we help the hospital predict on a daily basis how many, and on a weekly basis, how many beds they needed specifically for ICU, because they needed to go back and reopen, you know, some traumatology or cancer department, and they cannot do surgery unless they have an ICU unit available by regulation. And if all ICU units were taken by COVID-19 patient, they couldn't open. But with our predictions, they were very helpful. Because you know, they could predict like in a week we will have you know 10 free ICU units bed, you know, with some confidence intervals. Of course, we were giving them also confidence intervals, and so they started slowly reopening other department in the hospital, and they were very grateful. So it was the exact same model of the first paper. In an easier setting because we knew how, you know, patients were moved from each one of the category.
So in the end, the predictions were very close to what actually happened?
Yes, yes, yeah. Yeah, and actually in that case, the model was also presented to, you know, some ministry of whatever, like the director of the hospital presented our model. And maybe other hospitals used it. So this was right at the beginning of the pandemic where everybody was trying to make predictions. And so at the same time we were developing this model, we realized it was useful also in that setting. So we were doing both type of predictions. Thanks.